butterfly picture is just an amazing picture. Right, let me just get this.
I wouldn't call it stunning. What is it? Now cast your clout till May is out.
It's dead right, isn't it?
But May is out. May's the hawthorn. That's out.
Amazing.
Oh.
There we go. Right, we're on there. Okay. Okay. Yeah. Okay. Can't say. Sorry, Kate's just asked me something. 26. Yeah. Okay. 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 Just want to make sure that we're on YouTube. Yep. We're on there. Excellent. Sorry, everybody. I'm just checking as we're broadcasting everywhere.
Trustees of museums and galleries. This is
I want to see my background.
Hello, Philippa.
I can't see anybody.
Oh, we're here. I think it's
We
you.
can see you.
Have I got my background of Madeira?
No.
Oh,
No,
well, that didn't work then, did it?
Nice try.
I've set all these backgrounds and I don't...
What is it you're using, Philippa? Is it a laptop or iPad?
Yeah.
You should have you've got a background option on there or not?
Yeah.
I want to see my background.
Hello, Philippa.
Well, my background's the view from our apartment.
Over here.
Well, that's... How do I do it then?
Go to video. Wait. Video. Stop video. Start video.
Just so everybody knows, we're currently live on YouTube. Okay.
Oh, sorry.
That's all right. No, it's fine. just so you know.
No, I went into my settings and I put about a dozen different backgrounds to choose from. And I left it set on the view of Madeira Harbour. But obviously, I can't even see me anyway. So well, how can anyone
Go
see
to
me?
where it says, start video, stop video in the bottom corner and click on the little arrow. It gives you the choice to choose the virtual background.
Oh.
And everybody, I've been very rude. I haven't introduced.
Right, okay.
So,
Well, where are they now?
say hello. Most of the people that we've got on Zoom, they're members of the society or members of the committee. So Eddie's in Switzerland. So they are just going to say hello to Eddie, just introduce him first.
Can't see.
Okay, we've got a couple of minutes. I'm just going to wait for others to join us.
What's all these strings?
That's what I've just put on, fairy lights.
We can hear you. We can't see you now.
Yeah, probably a good thing.
I've got fairy lights. Can I get fairy lights off?
Simon.
Yeah. Hello, Graham. How are we doing?
I'm good. Yeah.
Good to see you.
Good. And you too. Yeah.
Okay. I'm just going to give it a couple of minutes, everybody,
Okay.
because just going to let everybody get in and join us. We've got people joining us on YouTube as we speak.
I've got to start video.
Oh, Philippa, that looked like you were on telly.
Yeah, but how can you? I don't know how you can see me.
I
can
can
only
see
see you,
you're
Linda.
framed by a television or a mic, or is it microwave?
Oh yeah, it's a telly. I'm playing now. Sorry,
I haven't downloaded. I must download some pictures then.
I have, but these aren't mine, obviously. Oh, I want my pictures back.
Just give it another couple of moments. Just wait for people to
Let's do it now.
come on. Eddie, you okay? Just waiting a couple of minutes just while we wait for people to join
Sure,
us.
no problem.
Good man, thank you.
It wasn't the phrase, "Are you sitting comfortably? Now I'll begin."
Yeah.
I don't have a green screen. Oh.
Oh dear, Philip has found backgrounds.
We haven't.
No, I haven't. I can only get this
Thank you.
telly.
So you need to go to none. It'll give you, there'll be a, I think there's
I'm
a
trying
circle
to.
with there's a circle with a line through.
I'm doing it, but
Circle the line through.
I'm doing none, but it's not. It's stuck on this telly now. Oh,
Well, you always wanted to be on the telly.
no, I didn't.
So,
There we go. Right.
Go on,
I just want my photos back then. I'm disappointed now.
Okay. We've got
Okay.
more people coming in.
None.
Just as about to start, more people joining, so give us a mo. Yeah, it has been a horrible day, hasn't it?
Mm.
No,
Well,
that's
I've
been
had
compromised.
my second jab.
Did you?
Mm.
And how do you feel?
Fine, no
Yeah.
problem. Mm.
Was that today, Linda?
Yeah,
No,
Yeah.
likewise, this afternoon.
Yeah.
Excellent. I seem to be getting through them, don't they?
Mm.
Yep.
Brilliant. I'm hoping my second doesn't make me feel as bad as the first did.
It won't.
Won't
No,
it?
they say
No.
it doesn't.
No.
Good.
Mm.
I hope not. It was only 24 hours, but
We had it. A lot of people have said they've been fine after the second one.
oh, really?
Yep.
Good.
I was lucky, fine after the first as well. So
Oh, I can see who Mum is now. Hello, Mum.
My mum.
yeah.
Yeah.
Okay, I think let's have a look. Okay, I think we're ready to go. Right. Are you happy, Eddie, to kick off?
Sure.
Yeah, brilliant. Okay. Good evening, everybody. Great to see you here this evening. Thanks for joining us here at the Womben Scientific and Historical Society monthly talk. It's good to see you live on Zoom and on YouTube as well. If you've got any questions, then feel free to pop them in the chat window on Zoom or in the chat window on YouTube, and then we can put them to our speaker tonight, who is Eddie Burdak. Bit of Zoom etiquette. I'm just going to mute everybody who's on Zoom so that we don't fly around all over the place with noises in the background and then the picture flipping to everywhere. So just so as you know, I've just muted everybody off. Yeah, our speaker this evening is Eddie Burdak. Now, Eddie's actually in Switzerland at the moment, and that's where he lives and works. And I'll let Eddie tell you more about his job and how he came to be in Switzerland. But Eddie is a Womben lad made good. And Eddie escaped Womben a few years ago. I'm sure not that many, Eddie. And made his home and work in Switzerland. In fact, his mom still lives in Womben, and I know that he visits when we're not in lockdown. So Eddie is a specialist at Pilatus Aircraft, and again, he will tell you more about that. But I think without further ado, I'm going to hand you over to Eddie for tonight's talk, which I'm sure you will find absolutely fascinating. So, Eddie, the floor is yours, and it's over to you.
Okay, good evening, and thank you, Simon. So tonight, I want to talk about some theories of flight as opposed to the singular theory of flight. I'm going to attempt to demystify some things that have been said and reported in press, and not only in press, the way I learned about aviation, which I found really annoying, but we'll get to that. Who am I? I'm actually I work at Pilatus Aircraft Limited. I look after aircraft performance, from design, development, certification to operational support. But I'm obviously just one of many, many engineers. And so in aerodynamics, obviously, we love our airplane to be sleek, smooth, rounded. When it's offered to the air gets out the way, lets the airplane through. But when we give our design to our drawings to the design group, they look at what they can draw and produce. And invariably, it looks something a little different. When the stress group get involved to make the aircraft nice and strong, they obviously prefer something with iron girders. And you can imagine how this sort of builds up. If they have iron girders, it's all heavy. We need to get the weight group in there to make things nice and light again. So we keep fighting with various groups. It's a cooperation. It's a very difficult berth. As you can see, the power plant group, they only think about one thing. And so airplane design is a compromise. Now, I am presenting this from one point of view. What you're going to see tonight is from my point of view only. I'm not representing the company I work for at all. I'm not representing any aeronautical bodies I work for. I got dragged into this by people asking me questions about things that were getting reported in the press. And I thought, you know what, it'd be good to try and get this out to the, to get an understanding out to the general population. And I thought, yeah, Wombin Historical, and where else are you? So I thought you guys would actually be quite a good audience for this presentation. So we're going to talk a bit about the science side. Where I'm going to start is on the subject of lift, but I'm going to touch on your historical part by starting on a grassy knoll in Yorkshire, where the landowner, one George Cayley, who has been studying aviation for decades. He'd been studying many aspects of aviation. He loved watching birds and how things flew. And when he's about 70 years old, he came out with a design, this governable parachute. This is circa 1853, and as I say, Scarborough, Yorkshire. And he was a bit old to get into this thing. And so he volunteered his coachman, one John Appleby. And the reason he did that, at least the story I've heard, is that this glider was going to be pulled by a horse because he wanted to demonstrate the forces of flight. And it actually flew. It flew 900 feet. It crashed. Mr. Appleby was given basically, this is looks like a boat with spoke wheels, and it looks like a tiller. And this is actually to supply control that he can try and make this vehicle pitch up, pitch down, go left or go right. But I can imagine it's offered him no control whatsoever. It crashed after 900 feet, but John Appleby, the coachman, survived. And by the time George Cayley managed to get over to speak to him, great big grin on his face that this machine actually flew. The story is that John Appleby asked to be relieved of his services because he was actually hired as a coachman, not to fly. Now, the thing is, this is where the forces of flight come from. So George Cayley determined that if the heavier than air machine had a center of gravity roughly where the person sits, it must have a weight acting down. Then, from his Isaac Newton's theories, applying Newton's third law of motion to every action must be an equal and opposite reaction if this vehicle is to fly level. So there must be a force called lift acting in the opposite direction. Now, for the non-physicists, Newton's third law is basically the one that says never ever kick a door, because a door will kick you back with equal and opposite force. So you'll know about it that way, but the physicists will understand Newton's third law. To every action is equal and opposite reaction. To generate the lift, the vehicle needed to move forward in the air, and there were some experiments that George Cayley did on that, which I'll get to briefly. But how was he going to do this? He was going to do this by using a galloping horse to drag this thing forward and give us some thrust. But again, applying Newton, there must be a force equal and opposite to that, which he called drag, which would prevent the aircraft from flying faster and faster or slower and slower. It would fly at the same speed. And these are the forces that we use. This model is basically the core of my work, to tell you the honest truth. Now, you might think this is a flight of fantasy, but now you guys are getting out of lockdown, try going up to the Yorkshire Air Museum, because there is a mock-up, it's a mock-up of this. It's not the original, because the original's finished up in pieces, and they do fetch it out on a nice, fine day. You can read more about George Cayley on the Historic UK.com website. Simon should have posted some links up, or will post up some links. To learn more about George Cayley and the things he did, because he was a great aviator, I would suggest that you check out the second link from Vimeo. And that is because this was a presentation done by the BBC by a chap called Marty Jobson. I don't have time tonight because I've only got 6 minutes. Because it takes 6 minutes, not I've only got 6 minutes. I'll push on, but I do recommend that you guys check that out later on when you've got time. So moving on, I want to take these forces and look what happens. So if the vehicle took a second person on board, increased the weight, then the lift must increase as well for the vehicle to stay straight and level. But the thing you don't see is there is a connection between the lift and the drag. As lift increases, the drag must increase. That's the way it works. But if drag increases, you're going to have to increase the thrust. Now on an airplane, that means either opening the taps, putting in more fuel, or putting in a bigger engine, or both. But all that means is you would actually increase the weight. And of course, that brings us back to the beginning. And so it's a very difficult, a very tender relationship. It's a love-hate thing that goes on. But fortunately, this process is reversible. As your vehicle gets lighter, as you consume fuel, then the aircraft will go faster. In fact, you probably have to finish up pulling back the throttle in some cases. Now, that's all okay. That's what lift is. But where does it come from? So there are a number of theories when I was studying, a number of theories where lift came from. And to explain this one, this is a longer path or equal transit time. So air is offered to the aerofoil, and the air particles, the blue line goes above, the red line goes below, but they meet together at the end of the aerofoil. They separate at the start, but meet again at the end. Now, when I was being taught this, I was thinking, well, how are the molecules connected? Is there a rubber band or something? Anyhow, the thing is, this is a theory we were taught, and because you've got to go a further distance on the upper surface, you'll go with a higher velocity. And there was actually a Swiss guy the Daniel Bernoulli, and in fact the Bernoulli family are very interesting, who realized and worked out that the higher the velocity, the lower the pressure. So on the upper surface, you had a higher velocity, lower pressure. On the lower surface, you had a lower velocity and a higher pressure, and the difference between the pressures provided the lift. It is incorrect. Now, why I'm telling you this? Because I was forced to learn this at university as if it was gospel. And there are, as you can see, this is incorrect theory number 1. There are several incorrect theories, and I learned them all. And I have exam papers on them, and I don't know why I had to learn this. Let's show you how this is wrong. Now, I'm going to be handing over to a Professor Holger Babinski at Cambridge Uni, who explains this very well.
Lines. It's often said that lift on a wing is generated because the flow moving over the top surface has a longer distance to travel and therefore needs to go faster. This common explanation is actually wrong. This video shows that the air on the top does move faster, but it doesn't reach the end of the wing at the same time as the air along the bottom. Here we use smoke to visualize the streamlines around an airfoil. We can pause the smoke by briefly interrupting the supply. This gives us lines that travel through the flow, as we can see here. And if we now slow the video down, you can follow those lines, and that gives you an idea of how fast the flow is in different parts of the airflow. Here you can see it speed up as it approaches the airfoil, and it moves faster over the top compared to the bottom. You can see that it reaches the end on the upper surface much earlier than it does on the lower surface. In fact, by the time it reaches the end on the lower surface, the flow's already gone a long way past on the upper surface. This shows very clearly that the flow doesn't take the same amount of time to reach the end of the wing.
Okay, so in fact, it's even faster. So that disproved the theory that I was showing you before. And as I was saying, said before, these were theories I had to learn, and instead of learning how lift is really generated. And I'm going to attempt to explain to you guys tonight in about 3 minutes how lift is generated. And if I fail, trust me, Prof. Babinski has got more videos. It'll take about 20 minutes to explain it, but it is worth listening to. If you recall, the flow around the airfoil cores the air. These lines are equal. Imagine these lines as the smoke particles, cause the flow to bend around the airfoil in a downwards fashion. Now, if we look at this a little closer, that means as the particle of smoke is going along the arc, that the pressure on the outer part of the arc must be greater than the inner part of the arc. So the pressure on the outside is greater than the pressure on the inside. If it was the same, the particle would continue in a straight line, according to Newton. And if the pressure on the inside was greater, the particle would actually deflect upwards. So we know that the pressure on the outside of that arc must be greater than the pressure on the inside. If you imagine we're far enough away from the airfoil at the top that we are at ambient pressure, that means each time we're coming in, we are reducing pressure. This pressure is greater than this pressure, is greater than this pressure, and so on. So the upper surface of the wing, we actually have a lower pressure than the atmospheric, and the opposite arguments can be made for the lower side. So you get a higher pressure than ambient on the lower side, atmospheric on the lower side. And so the lift is simply the difference between the pressures between the upper and the lower. So the incorrect theory you saw before has the right explanation, but it's achieved it the wrong way. And yes, you only get lift if the flow bends. If the flow doesn't bend, the only thing you're getting is drag. And the flow will bend based on the speed of the flow and the shape of the objects in the flow. And that, in a nutshell, is where lift comes from. Okay, so now I think I've given you enough on the physics side with regards to lift, the importance of weights. What I want to do is bring you bang up to date now, and we start talking about emissions, because this is a very topical subject at the moment, and people are making some extraordinary claims, and we're going to be examining some of those claims. So what are emissions? If you imagine jet fuel as a hydrocarbon, so that's basically carbon and hydrogen atoms joined up in the molecule. From fossil fuel, we get a lot of impurities, and one of the main ones is sulfur. In the other end of the engine, we throw in nitrogen and oxygen, basically air. So out the back, you're expecting to see a combustion process which produces carbon dioxide, water, and sulfur dioxide from the impurities. But in fact, what we get are several other things. We get oxides of nitrogen, oxides of sulfur. We get unburnt fuel. This is hydrocarbon, which is unburnt fuel. We get carbon monoxide. And in some cases, you can get black carbon, which is soot, but just carbon. Now, what's extraordinary, I find, is looking at this figure on the right-hand side, is for every 1 ton of kerosene we throw in, we produce 3.15 tons of carbon dioxide and 1.24 tons of water. The other impurities that come out the back of, or the other emissions that come out the back of the engine are relatively small, but we put in 1 ton of kerosene, burn it, and we're getting more than 4 tons coming out the back of the engine. You can't create matter, can you? Well, let's examine this a little more careful, but this means I'm going to be pushing you on a bit of organic chemistry, and you might have some nightmares about that from, well, I might have had some from ourselves. So kerosene there is no simple molecular description for kerosene. It's made from hundreds of different hydrocarbons, paraffins, olefins, aromatics. There's no simple formula. And on top of that, in the aviation world, we throw in things like icing inhibitors. We can't afford the fuel to ice up. We throw in corrosion inhibitors. We don't want it chewing our tanks. And biocides, we don't want algae growing in there. So it gets very difficult to examine it from a pure chemistry point. But what I'm going to do is simplify the problem. So let's look at it as a hydrocarbon, and just looking at a segment of a hydrocarbon molecule there. So we have a chain of carbon atoms which are linked with each other, and hydrogen atoms attached to those carbons. Fuel, of course, has benzene rings and other things in there as well. But what I'm going to do is simplify the problem even further. I'm going to just take the one segment. I'm going to plonk that segment over there, and we're going to start looking at some molecular weights. So if I look at the hydrocarbon here, CH2, and add up the atomic weights for the hydrocarbon, I'll finish up with 14 units. If I now look at replacing those hydrogen atoms with oxygen atoms, I'll finish up with 44 atomic mass units. And if I divide this 44 by the 14, I'll finish at 3.14, which is very close to this 3.15 value over here. I do the same with the water, because the carbon here, the hydrogen's got detached, oxygen's gone there, and now the hydrogen will attach to oxygen, forming water. And I get a similar values again. I'll get 1.28 over here compared to 1.24. Now, anyone who does carbon offsetting will see a figure of 3.16 in the aviation world, maybe 3.15 elsewhere. So this figure, 3.16, you multiply by the weight of fuel that you are consuming, and that tells you the amount of carbon you need to offset. So if anyone looks into carbon offsetting and sees this number 3.16, it is not a made-up number. It has some chemistry behind it. I have oversimplified the thing tonight, but it gives you that it's broadly a correct number. And there could be some other influences in there. They may have considered adding, oh, well, we've got to consider the airport, the fact that we've got concrete on our airport and things like this. I honestly don't know, but 3.16 is the figure that's used in the aviation world. Now, I want to look at some of the minor emissions first, and I say minor in a broad sense because they are things we still need to worry about. One of the other emissions was sulfur oxides. The X can represent 2, 4, whatever number. Sulfur is, as I said before, is an impurity within the fossil fuel. Sulfur dioxide can affect air quality, and this means it can cause you problems to breathe and things like this. And sulfur dioxide, again, in the air, high up, it can combine with rain and form acid rain, attacking our ecosystems. And I do remember in my youth that you could actually get fuel which was sulfur free, but you had to pay more for it because you've got to do another process to take it out, and no one bought it. So I don't think they actually took too much. I think they took it to heart and decided not to offer sulfur-free fuel anymore. Nitrous oxide. Oh, and before I carry on, sorry, sulfur oxides can occur naturally, but usually only in things like volcanic activity. Nitrous oxides. Well, where does the nitrous oxide come from? Nitrogen is normally quite an inert gas, but it's formed by combustion. Once you heat or set fire to something, nitrogen gets rather excited and will want to bond, and it's formed by this combustion process. And nitrous oxides are, well, they have huge influence on our ozone layer. So in the upper atmosphere, towards the stratosphere and so on, ozone, you may remember, well, we want ozone layers because it does things like blocks the ultraviolet radiation. You may remember from the past, we had the problem with aerosols eating into our ozone layer. But we don't want ozone at the lower layers. In the lower layers, together with interaction with other chemicals, it forms smog. And again, we're back to air quality and being able to breathe. I remember being in London thinking this was pretty bad because out where I am at the moment, I'm not in a huge city where we get lots of nitrous oxide produced. The thing about nitrous oxide is it also gets formed naturally, and it gets formed, as I say, in combustion. So it also gets formed in things like lightning flashes. And maybe Simon, our weather chap, can talk about this a little bit later. But as far as I can tell, there's more than 1 billion lightning flashes across the planet in any given year. In fact, you can see a lot of activity in various places. So a lot of nitrous oxide gets formed in the atmosphere naturally, but we are concerned about nitrous oxide as an output. It's one of the things we're heavily trying to avoid putting out in the aviation industry. So I've talked about the minor emissions. I'd like to talk briefly about the major one, carbon dioxide. And again, a lot of things are said and misunderstood here. In the transport sector, if we look at it versus the rest of where emissions occurred by sector, transport gives about 22% of the carbon dioxide on the planet. And aviation is 11% of that 22. So approximately 2.4% of the carbon dioxide out onto the atmosphere. And I'm only talking about carbon dioxide mass. I'm not talking, oh, if you release it here, it should be counted more significant. I'm just talking about just basic mass at the moment. So about 2.4% of the emissions comes from the aviation sector. And what is sadly misunderstood is when you look at business aviation is only about 2% of the civil aviation. So when people get upset about business aviation, they're actually getting upset at about a figure of less than 0.05% of global CO2. And frankly, I think there's some bigger things that need to be addressed. But I do have a biased opinion because I do work in the business aviation. But let's move from percentages to actual values. What is this? So I'm looking here at the fuel consumption in billions of gallons versus the last set of years up to 2019. And you can see there's a rise going on. There was a dip back in 2008 and 2009, and I guess there was some sort of banking crisis, as there usually is, which represents a dip. But you can see we're heading to 100 billion gallons of jet fuel per year. And when I look at numbers, I like to have some sort of feeling, some sort of sense of those numbers. And when they're so big, you normally lose all sense of feel for the numbers. COVID has actually hit the numbers quite hard, but I'm not worried about what COVID has done at this point. I want to focus on the 100 billion gallons. What does 100 billion US gallons look like? Well, that's 2 billion bathtubs, but I still struggle with that, but that's too big a number for me, 2 billion bathtubs. What else could that look like? Over 151,000 Olympic-sized swimming pools. Hounsdale doesn't have an Olympic-sized swimming pool. What else does that look like? Chase water reservoirs, 86 chase water reservoirs going up every year. Or six and a bit Lake Verney's. Now, if you accept what I was saying before, that aviation is 2.4% of the global CO2, then what we're putting in the planet is 3,585 chase water reservoirs worth of fuel, or 264 Lake Verney's. So when people argue to me, oh, how arrogant is man that they think they can influence the climate, I struggle because I don't see how we can't be affecting the climate. And remember, this is 1 year worth of carbon dioxide we're pumping out. And we've been filling the planet since, well, the Industrial Revolution was 250 years ago. We've been filling the planet ever since that period. And yeah, it's huge. So what are we going to be doing about it? Okay, so I want to introduce you to an organization called ICAO, the International Civil Aviation Organization. They are the United Nations of the aviation world. And so they set out global policies, global mandates, and each area, each local authority, like in the UK, you have the Civil Aviation Authority. In Switzerland, we have the Bundesamt für Civil Luftfahrtwerk, or BASL. Each body can define higher standards than what is defined at international level, should they so desire. And what ICAO look at are things like, well, the security, airports, economic development for countries, capacity, but they look at safety, which is our #1 primary concern, and they're looking after environmental protection. Don't know if you remember, but back in the 60s, we had turbojets, and the noise from the turbojets was just immense. In noise protection, that falls under environmental protection as well. Now, you saw earlier how we saw a climb in the consumption of fuel. And so if we look at, and here what we're looking at is the net CO2 emissions in megatons over the forecast period over the next 25 years, then if we plant ourselves at a point in 2020, this black line represents the projection of air transport, and we were reckoning a doubling of the transport within the next 15 to 20 years. Now, this is all pre-COVID, so I'll talk about that a little later, but we're working to these numbers. COVID has maybe shifted this graph to the right a bit, but we're still working to these numbers, and we're going to be trying to resolve this issue. How are we going to resolve this issue? Well, what the aviation sector said was they want to do carbon neutral growth. How are they going to achieve carbon neutral growth? They're going to use a set of basket of measures. And in that basket of measures, we've got aircraft technology. So we're going to be trying to make the aircraft lighter. You saw the importance of weight earlier. We're going to be trying and improving engines. As you saw, we have unburnt fuel that's managing to get through the system. We're going to try and improve how the fuel is consumed. We're going to try and make the aircraft cleaner. So aircraft technology, we're hitting this every time. We're always trying to improve, but we were always trying to anyhow. But now we have a more emphasis. And if you go back to the disclaimer I had at the beginning, where we have this set theory where we could put all the engineering teams in, what happened was on the right, we had the loft group, production group. And if you want to make your airplane cheaper, you push the scale that way. But if you want to make your aircraft more efficient, you push it back the other way towards me in aerodynamics. That's one part of our basket of measures. Operational improvements, I don't know if you remember, but there used to be time that you would go around, you would be in the airplane, you'd be waiting to take off. When you arrive at your destination, you could be put in a hold. That doesn't happen anymore. When you go in an airplane and you go to take off, there's only like 2 or 3 airplanes in front of you, not 10 or 20 as there used to be. When you take off, you can only take off if you've got clearance to land, so you don't hold the destinations anymore, so we burn much less fuel. When you're on the ramp, when you're on the apron taxiing around, you don't taxi on 2 engines, you taxi on 1 engine. So operational improvements will bring us some way down as well. But as you can see, with both aircraft technology and operational improvements, it's not going to do enough. So we're looking at a thing called sustainable aviation fuels and CORSIA. What on earth is this lot? So sustainable fuels. We're talking, this is from British Petroleum. We're talking taking household waste, such as cooking oils, forestry waste, and putting that into feedstock. And this feedstock will get converted to an oil, which can be then converted to a, can be then later refined into various levels of fuel. That fuel, at the moment, we mix it, we blend the fuel with existing fossil fuel, and it can then get used in the aeroplane. But there's another quite interesting way of getting sustainable fuel. And we're going to listen to what's going on here, because this is the source of where this presentation started.
Why don't we recycle energy?
You're hitting the nail on the head. We would like people to be recycling their fuel in the same way as they recycle other things.
Your technology is we're going to refine that energy, that carbon out of the atmosphere, combine it with hydrogen and water, and then that's the same as gas or jet fuel?
Yeah, it's chemically the same. No pollutants. So for example, our diesel burns completely clean. None of that black smoke you see from trucks when they go up hills,
right.
Completely clean. But yeah, it's chemically identical. So this is our plant. Great to have you here. Everything here is a working model, full process working, and we are capturing CO2 from the atmosphere right here. Think of it as like a big cooling tower. Large fan, the fan draws the CO2 in, chemical reaction, and we capture the CO2.
Wouldn't there be more carbon to capture by dirty, naughty factories?
No, it's uniformly distributed.
So
we could put one of these plants in the middle of Beijing, or we could put it in the middle of the Sahara Desert. You would capture the same amount of atmospheric CO2.
So we as a species have put it in, so we as a species should be taking it out.
Well, that's our choice, but I think we have to, or find somewhere else to live. This is the fuel that we make. It looks exactly the same as any other fuel.
Right.
It's very, very high chemical performance,
right.
Higher performance fuel than the stuff you buy at the pumps today.
So it's better than the pumps, it's carbon neutral, and theoretically it would be cheap to make because you're refining the energy that's already out there in the atmosphere.
Yeah, you're using the CO2 from the atmosphere. Your only feedstock, the only thing you're consuming is renewable electricity.
Right.
But here's the interesting thing. A carbon neutral fuel that's compatible with any vehicle in the world today.
Right.
So that car you just drove up in, we can make that carbon neutral tomorrow.
Wow.
Any vehicle, any performance vehicle, any battered old truck, aeroplanes, we're compatible with all of those. Which is significant because nobody's making electric tractors or electric planes.
Right. Do you have to do any modifications?
No. What that? So transportation is about 20% of the CO2 emissions. How are we going to decarbonize that? There's 1 billion cars in the world. So if we all go electric, $50,000 for an electric car, that's $50 trillion. Then you've got to deliver energy and electricity to each car. It's a massive change.
Yeah.
Alternatively, why don't we just change the fuel? The price to you at the pump will be the same.
Having something like a carbon neutral gas isn't even enough. We've got to start going negative. We've got to actually pull carbon out of the atmosphere. Now, can this do that? And what's the
You
plan?
can take the CO2 generated here and bury that underground, and you get to negative emissions.
Right.
It's a hugely important thing.
And how many do you need to scale it to get to carbon negative?
You need less of these than there are power stations in the world today to net emissions out to zero.
And how many is that?
It's in the region of tens of thousands. If we are taking measures as we should be to remove emissions elsewhere, now you start getting to an overall negative emissions from the world.
Why isn't the world rushing to Squamish, BC and saying, can we please make 100,000 of these?
So first of all, we're open and ready to receive the world. Secondly, we've really just got to proof of concept here, and it's working. So the next step for our business is to expand across the globe, make carbon neutral fuel, and when the scientists and the governments decide that they need to do negative emissions, the technology is ready.
Okay. So that all sounds really quite exciting. And I picked up on a few things I'd like to discuss. So let's go through some of these things. Burns completely clean. Well, if I remember right, normally if a truck's burning black smoke, it's usually that the fuel is not burned properly or injector performance. This fuel will not solve fuel injector issues. It will burn differently, so it may not be as black. And he's not got in this fuel the impurities we have in fossil fuel. So I'm hazy on this one because I understand where he's coming from in principle, but I would like to see this in a battered old truck going up the hill. And so I've got a little color code down here. So dark green is hazy. I think I know where he's coming from, but I don't quite agree 100% with him. And that's because I'm a pedantic person. Carbon neutral. Well, neutral for carbon dioxide, yes. But if you remember, we had other carbon sources. We had carbon monoxide, we had unburned fuel, and we had soot. So he's neutral for CO2, and CO2 is the biggest contributor. The other ones are less so, considerably less so. But again, if he wants to claim carbon neutral, I'm a little hazy because again, there's bits of pieces of other carbon which aren't being taken out. Compatible with any vehicle, as long as it meets the fuel standards of that vehicle, absolutely. And here, I'm in full agreement with what he's doing. No one makes electric tractors or electric planes. Well, that's an interesting one. Electric tractors, you can buy them today. You don't even need to sit in them. I don't know when these tractors were available, and I don't know when Steve made his claim, but there are plenty of, well, not plenty, there are electric tractors out there doing some fantastic stuff. Electric planes, that's an interesting one. So let's have a look at electric planes. I'll get to the chart in a moment, but let's have a look what we got. This is from Zoom. They have investment money or had investment money from Boeing, but Boeing have run into trouble and pulled the plug. Zoom at the moment, I don't know where they're going, what they're doing, and so that project at the moment is on pause. This project over here, Alice, is an Israeli product. They had an unfortunate incident with their first prototype. No one was hurt. And the second prototype, I believe, is either about to fly or is flying. They're pushing ahead. It's looking interesting, but as an aerodynamicist, I do worry about the position of some of their engines. The really interesting one, though, is the airplane at the bottom. This is from Airbus. It's the old, well, BA Systems will get upset, but it's actually a Hawker Siddeley 146, but they'll say, no, it's a BA RJ 100 or something. What they're planning to do here on the 4 engines is take one engine out, convert it to a fan, which will be powered by an electrical generator. And this was going to be, if I remember right, 2 megawatts. And this was quite an exciting program. And Airbus was scheduled to actually start flying this, I believe, this year at Cranfield. But they've cancelled this program because of COVID. And I think they cancelled it because they were probably pressed, because they probably finished up going back to their government looking for subsidies, because the airlines aren't earning money to pay back for their aeroplanes. And Airbus are doing something else. So, you know what? In principle, I have to agree with Steve. There are 1 or 2 smaller electric airplanes, which I'll get to, which are in production, which are certified. But in principle, I've got to agree with Steve. And what is the problem with batteries? Well, on the left is a horrible chart. I'm looking at energy as a function of density and energy as a function of volume. And batteries are down here. They're low on energy density, whether you measure it by per litre or by kilograms. They're just not up to the job, not for the large scale aircraft. Hydrogen, we're going to get to a little later. Liquid hydrogen has fantastic energy density, but again, doesn't have the volumetric density that we require. Gasoline is in there. You really want to be up in this area of the charts and not down here. So you may have seen some developments in the industry where they're talking about urban air mobility. And it looks like nothing more than a collection of quadcopters. Now, these quadcopters, they're all going to be electrical driven. It's air taxi and all this. It sounds wonderful. But frankly, the ones I'm seeing here, apart from the one you're seeing flying, the other ones, well, except this one here, the other ones are just working with helicopter blades. They're not taking advantage of lift. Lift is important. It's doing work for you. Put a wing on the design. So this is where this one scores. That's Lilium up there, which is being done up in Munich. And this one is Joby, which is in the US. And the thing is, there's quite proliferation of these. There's actually more than 10. So it's probably approaching about 100 different designs of urban air mobility. And they're all working with electricity. But when you get to your destination, what are you going to do? You're going to wait the next day to charge the batteries? You're going to swap the batteries out? It doesn't, to me, it doesn't make sense as a business case. The air vehicle needs to be out there working as much as possible to earn its keep. So when it comes to electric aeroplanes, I have to agree 100% with the claim that Steve made. No one's making it. They're trying, but it's not working. Electric tractors, no, they're there. No modifications to your vehicle, absolutely. And this is like the Holy Grail. It's a drop-in. You may hear the term drop-in solution. And then the price at the pump to be the same. Well, this isn't Steve's direct air capture. This is using biostock. But currently, they're 3 to 5 times more expensive. And we do blend them, which will help bring the price down a little bit. But at the moment, sustainable aviation fuel is not a big thing. It may come down with economy of scale. There's companies such as Gulfstream who have been operating for over 3 years. They've done 550 flights, flown 1 million miles on sustainable aviation fuel. We need to prove that the fuel is not eating the tank, it's not eating the fuel system, it's not eating the engine, that it works. So we need to get a degree of reliability measurements into this. So that's my take on what Steve's been talking about. The interesting thing on the direct air capture, though, is he will go to, or can take air carbon dioxide out of the atmosphere and bury it. Now, ICAO, the other thing after sustainable aviation fuels was CORSIA. CORSIA is Carbon Offsetting and Reduction Scheme for International Aviation. And it's in the pilot phase at the moment, and it will be introduced probably in the next 3 to 4 years. And this means carbon credits, and carbon credits can be things like green projects, whether you invest into sustainable forest management, or reclaim forestry or invest into renewable energy projects. So there will be carbon markets, and you'll be encouraged to invest in them. However, there is no managed, monitored, accredited system today. And in 2007, some chap in Hungary, and well, I don't know where he was, not necessarily in Hungary, offered carbon offsetting for the Vatican in 2007. And he gave them a certificate. But the forest he said he was going to reclaim, which was in Hungary, never happened. And you can imagine how happy the Vatican are about that. And the Vatican weren't paying anything. This guy was just trying to get them on board to then advertise he's got God on their side. Now, batteries, what alternative energy sources can we have apart from the fuel? We talked about batteries. There's been demonstration flights around the planet. And here is a small aircraft that is certified and flying on batteries. In fact, it flies for about 15 minutes, including reserves. That's fantastic. But for the larger scale aircraft, it doesn't work because batteries just do not have the energy that we need. It's about 40 times less than jet fuel. And then what are you going to do? Normally, the airplane gets turned around within the next hour or so for the return trip. You can't lose time for charging batteries, and you probably don't want to swap out the batteries. The technology isn't there today, but that doesn't mean the technology won't be there tomorrow. I do know they're working on, I believe it's called sulfur iron, which is promising another step forward, but they've got to do more than an order of magnitude improvement, and it's a hell of an ask. So if we can't do batteries, if we can't store electricity on board, what about if we create electricity on board? Fuel cells. In fact, there's been a couple of fuel cell aircraft already. Boeing and Phantom Works have created an aircraft which they flew a few times. And recently in Cranfield, Zero Avia have been testing their aircraft. Hydrogen fuel cells have been around a long time. They've been around since the 1840s. And in fact, hydrogen fuel cells in the 60s have been to the moon and back. So it's not a new technology, but to get the energy out for the weight that they will be is a difficult thing. How do hydrogen fuel cells work? There's a very short presentation on that.
Have you heard about the new sustainable energy technology called fuel cells? In fact, they're really not that new. Fuel cells were invented in 1839 by William Grove and were developed by Pratt & Whitney and other companies in the 1950s. Safe and dependable, they were used by NASA and the Russian space program to power spacecrafts. Today, leading global companies like Apple, Verizon, and Coca-Cola use fuel cells to generate clean power. Honda, Toyota, and other car companies use them to power their new generation of pollution-free cars. So how do fuel cells work? Fuel cells use hydrogen and oxygen in a chemical process to produce electricity and heat. The only byproduct, pure, clean water. A fuel cell has two electrodes, an anode and a cathode, and between them, an electrolyte. The catalyst on the electrode breaks the H2 hydrogen molecules to allow them to combine with hydroxide, OH negative ions, to create water and release electricity. But unlike batteries, fuel cells don't store power for a limited amount of time. They generate it for as long as you have hydrogen. As a source of backup power, fuel cells are much better than diesel generators. They aren't smelly or noisy, and they don't produce harmful exhaust. Fuel cells can be used anywhere you need backup power. Mobile phone towers, electrical substations, manufacturing, and much, much more. Other green power solutions harness the sun or wind. But if you're caught up in a cloudy day or on days where the air stands still, these solutions can leave you without enough power when you actually need it. That's why you...
I'll pause there. He's about to advertise green cell, but I know my time's running out on me. So that explains briefly how hydrogen fuel cells work. Gen
cell.
And as I say, there's an aircraft that's been flying, and it's actually now starting to look at a nice sized aeroplane, a business class aircraft, with 250 kilowatts of total power, about 300 horsepower. just over 300 horsepower. And this flying down in Cranfield, or I should say was flying down in Cranfield. Just less than a month ago, they made a statement that their aircraft made a safe off-airport landing in a field just outside of the Bedfordshire airport. I'm not too sure normally what I would expect to see, but this is what a safe off-airport landing looks like. The crew were absolutely fine. They were battered, but they walked away from this. The hydrogen was secured. You can see there's no burning or anything there. It may have been to the moon and back, but apparently it can't do a lap of Cranfield Airport. Fortunately, and I really do think this is quite possibly a good way to go. Fortunately, these guys aren't deterred, and they are actually going to push on with the next aeroplane, because they had a family of airplanes they're going to work along. And I look forward to seeing the work from Zero Avia on this project. That said, I do love the understatement that's said there. And I don't know if you remember, but recently SpaceX lost Starship serial number 4 on the pad. It landed, and after a few moments, it's actually exploded. But of course, SpaceX won't say it's exploded. They actually claimed it underwent a rapid, unscheduled disassembly. And they do mean rapid. So I love my business because we actually do enjoy understatements. So, okay, what about hydrogen itself? Well, this is why Airbus have actually stopped doing or abandoned their EFAN-X program, the electric airplane we're looking at. And Pipistrel, who made that other airplane I showed you earlier, which is already certified, which was a battery-powered airplane, are looking to get into this market here. Hydrogen has already been tried. It has been tried back in the 1950s. And this, though it says it's a B-57, any aviation buffs out there will realise it's an English electric Canberra. And what they did was they made no modifications to the engine, but they were going to shut down that engine and feed hydrogen, which they did. And they had some problems at first, but eventually they got it to work. And the one engine that was running on jet fuel produced no contrails, no condensation trail behind the airplane. While the one working with the hydrogen, it just produced an enormous, dense and persistent condensation trail. And if you're on the military and you're sort of announcing your arrival, who needs radar? So the project got shelved quite early. The Russians actually looked at it in a couple of aircraft, which was a passenger aircraft, but that was back in the 70s, I think. I must admit, I don't remember exactly what happened there and why they abandoned it. What's so special about hydrogen? I've pinched this from an Airbus presentation from 1999, and we're looking at liquid hydrogen. So liquid hydrogen, for the same energy content, for the same energy by weight, I need 3 times less liquid hydrogen, but by volume, I need 4 times more liquid hydrogen than jet fuel. And I need to find somewhere to put it on the airplane. And we're talking liquid hydrogen. So I've got to put it, you've got to put it at minus 253 degrees centigrade. Bit of a challenge. Again, let's see what happens with an identical energy content. You're burning 1 kilo of kerosene, and you remember these numbers from before: 1.2 and a bit kilos of water, 3 and a bit kilos of carbon dioxide. For the same energy, you only need 0.36 kilos of hydrogen. There's no carbon dioxide output. There's no soot output, but we're producing 2.5 times more water, and because hydrogen burns hotter than the kerosene, we're going to be producing more nitrous oxide. And that is of a concern in this business. What would it look like? This was a minimum change aircraft that they had proposed. So you're talking about hydrogen tanks on top of the fuselage. It's starting to look more like a Zeppelin, and the romantic in me loves Zeppelins. But they concluded at the end of the day, they saw no real benefits with this. That was in 1999, 2000. Let's have a look at what Airbus think today. Airbus are now saying we can do hydrogen, or we pursue hydrogen aircraft. It's a hydrogen hybrid. What that means exactly, I don't know. They're going to be mixing the hydrogen with other alternative source, maybe hydrogen fuel cell and so on. But in that presentation, they talked about ranges of 1,000 plus and 2,000 plus nautical miles. Now, another day, I'll tell you about the nautical mile in its definition, but today I've got to push on. I have taken London Heathrow to try and see what these distances look like. And I've given Airbus the benefits of the doubt. They said 1,000 plus nautical miles. I've drawn a range circle of 1,500 nautical miles centered around London Heathrow. Now, it's a range circle. It may not look much like a circle, but the Earth is not flat. I've flattened it here for this presentation, which means my circle becomes sort of elongated, and the range circles will get funky. 1,500 nautical miles, I can do all Europe, I can get into North Africa, off to Iceland, Greenland, maybe, but I can't get anywhere particularly interesting. 2,500 nautical miles, the range circle gets really funky. And with 2,500 nautical miles, you can get to Newfoundland, but you'll need to either stop and change aircraft or something. You still can't get to places like Dubai, not that I've ever been, and you're certainly not getting to places like Australia. These are the kind of ranges they're talking about with these aircraft. What kind of range do we need? Well, if you want to get all Canada, and I apologise for the yellow line, if you want to get into places fully like Canada and maybe halfway through United States, you need 4,000 nautical miles, and this will get you pretty close, but still not quite to Dubai. Oh, sorry, I'm looking the wrong line. This will get you easily to Dubai. It'll even get you to Goa and maybe Mumbai in India. What kind of ranges do you need to get to like Australia? Well, you can do that today in a Boeing 777 or an Airbus A340. You need to get 8,500 nautical miles or further. And the range circle from London looks like it's more like a range circle around the Southern Ocean. And I do feel sorry for people of New Zealand because I did include them in my map, but they're still missing out. We can't get to them. So hydrogen is not going to get us as far as we need to get. So, Simon, I'm getting there. Summary. So, to summarise, just remember, please, this is my opinions that I'm just sharing with you. Sustainable aviation, we're looking at recycling carbon, whether it's bio-waste. One thing I think will be really interesting is algae or direct air capture, which Steve Oldham was talking about there from Carbon Engineering. What I do worry about is how big the plant has to be to produce the quantities of fuel required by the aircraft. There are desires that we move from 30-70 split on blends to 100% sustainable aviation fuel, and we don't use fossil fuel anymore, but it requires proving. Carbon offsetting, yes, it is good in principle and should be encouraged to contribute to reforestation or protect the forest or support renewable energy sources. But we know at the moment there's no accredited system. We need an accredited system. We need someone like the UN to step in here and set up some sort of body to say what is approved, what isn't approved. If you look at some airlines, when you book your flights, they offer you carbon offsetting. They tell you how they carbon offset. Some airlines actually do some good things. Some airlines do some bad things. The only thing I can say, and Steve will touch on it on some of his other presentations, Steve Oldham, and that is to make less trips. Make your trips a longer duration, maximize your effort, maximize your time from your journey, i.e. business and pleasure. So for example, that's when I usually come to the UK, because I will do business down in London and then pop up into Wimbledon for a quick visit. What I've got to do is convince the company, though, that we need business in somewhere like Mauritius. Then I can go and enjoy myself down there too. But that's harder work. Hydrogen, we looked at hydrogen. The problem with hydrogen is the nitrous oxides. Maybe that could be offset by burning instead of air in oxygen, because you're getting the oxygen from the hydrolysis, and then you're not burning it in air and not getting the nitrous oxide. But then you're going to be carrying more oxygen bottles, and it's all weight issues. I just don't see it working. I don't know how they're going to solve the nitrous oxide issues. Plus hydrogen, contrails, about 2.5 times more water. Clouds and global warming, maybe Simon can say something about this a little later. Clouds, they can trap the heat and warm. This is one thing we all know about, but we also know they can provide cooling to the planet. It's a love-hate relationship with clouds and contrails. And you've seen the range implications earlier. So batteries alone, we know just doesn't work. Maybe for small aircraft like Simon flies around in Halfpenny Green or whatever it's called these days for going to the business airport. Fuel cells and batteries for larger general aviation aircraft. That's something I think that may come, and I hope Zero Avia pick themselves up and crack on with it. But whichever path is pursued, expect costs to fluctuate. When Corsair comes in, airlines are going to have to offset their carbon, whether they do this by buying sustainable aviation fuel or buying carbon credits on your behalf. Your ticket prices are going to go up. If you with hydrogen, you would have longer trips or stopovers, but maybe a tactic should be used: liquid hydrogen for shorter trips and sustainable aviation fuel for longer trips. And but importantly, we can't do this in a rush. We're a safety first industry, and it's not something that we can take lightly or do take lightly. So it's not something we can change the world straight away. No, you got to do this right now. It doesn't work that way. It's got to be proven. And I'm sorry I've taken too much time, Simon. It's back to you.
Thanks, Eddie. That was absolutely fascinating. No problem with the time at all. Could have listened on and on to that. Fascinating. And I think you've given us a whirlwind tour there of aviation and of where it's going in the future as well, and the considerations that we all need to have. Certainly, lots of interesting points made, and I think lots to ponder for the future. If anybody's got any questions, please do post them in the chat, either on YouTube or in Zoom. We've got one coming from Ian Sadler saying, what do you make of the claim that the Wright brothers weren't really the first to fly? The launch ramps they used means they were aided, and the first real unaided flight was by Santos Dumont in France. Now, interested to know what you think of that, particularly given what you said about George Cayley and how that fits in with things. So what do you think of that, Eddie?
I'd actually have to go back and check on that one. Yeah, it is slightly debatable. The Wright brothers get the popular votes. They're the ones that appear left, right, and centre. Yeah, that's all I can say on the subject. Yeah. To tell you the honest truth, because I'll tell you, I'm sure there are others. Yeah,
is it a definition of what flight is as well? And I suspect it is.
It is. I mean, the Wright brothers was claimed to be the first powered flight, I believe. The Santos one, believe it or not, I'm not familiar with it. I'd have to read up on Santos and what he did.
Yeah, I mean, I've got that wonderful source of Wikipedia up here. I was just looking at it, and says that he was a Brazilian inventor and aviation pioneer, one of the very few people to have contributed significantly to the early development of both lighter than air and heavier than air aircraft. So yeah, that's
you know what? I have to get back to you because I actually work with 2 Brazilians in my office. I'll ask them for their opinion.
Yeah, they'll think he was the first. They'll think he was the first.
By definition.
But you were saying there about George Cayley. That's one that I'm going to have to go look at and have a look at as well. Because you did say that he actually did manage to fly.
It flew 900 feet. I don't think it was controllable. I guess John Appleby probably moved in the boat. and I imagine his centre of gravity affected the motion.
Do we know anything about the altitude he achieved and what height?
I don't know the altitude and height. In fact, could you go up to Yorkshire Air Museum and find out for me?
That's what we need to know, isn't it? If we're defining that's what we need to know.
I guess he didn't achieve too much height, but I'm sure the wheels cleared. And in fact, one of the interesting aspects of the KD vehicle was I'm not too sure when spoke wheels came about, but he had spoke wheels on that.
Interesting. Okay. Anybody got any questions? If you want to ask via Zoom, just unmute yourselves as well, and you're more than welcome to jump in. One that I've got, Eddie, just going on to the sustainable fuels side of things. I know that there's a lot of work underway at the moment with sustainable fuels and looking at sustainable fuels for use in motor cars. And I'm guessing that it's a very similar sort of research topic to sustainable fuels with aircraft.
Yeah, well, essentially it's the same thing, just refined to a different level. So once you get the basic crude, you just have to refine it to whatever level you want, whether it's for the car, whether it's for aviation and so on. It's just a different cracking point.
Because am I right that the aviation fuel that goes into light aircraft at the moment is effectively high leaded, high octane fuel that we used many years ago? That's still going into.
I believe so. Yes.
This isn't it? Yeah. It's because it's 100 LL, isn't it? So it's just it's the old 4-star higher leaded, higher octane fuel.
I believe so. Yes.
Yeah, because it does seem that the sustainable fuel, the synthetic fuel, seems to be an answer that has only started to perhaps come about in the last couple of 3 years. That's realistically looking like they could get production into the sort of quantities that we'd need.
The interesting one with algae, and there was a presentation by a guy from Boeing Phantom Works I attended. He was saying that if we could take algae, and I think basically he stressed the algae to produce the crude. He's saying you only need an area the size of Belgium to produce enough fuel for the aviation sector. And algae, it sounds like a good idea to me. However, if you want to look at it from the more from the climate and CO2 perspective, we're just recycling. And as Steve Oldham will tell you, is we need to take carbon out of the air. We need to stop. Recycling is a start, but at some point we have to take the carbon out of the air.
Yeah, we've been sticking carbon into the air willy-nilly for well over 100 years. And just stopping now won't undo the damage we've done in that 100 years.
Absolutely.
Yeah.
You're absolutely correct.
I think they had the technology to actually take carbon out the air for a long time. It's just they haven't developed it because of the money from the oil industry.
Well, it isn't just that. At the moment, taking carbon out of the air requires more power to go in than you're saving the carbon.
Yeah.
Yeah, this is the point. When you're doing things like the hydrolysis to get hydrogen out, absolutely right. The energy you gain from the hydrogen is much less than the energy you're probably putting in to get the hydrogen in the first place. So whatever we're doing, we're going to need energy to solve the problem, and we're going to be consuming a lot of energy to do that.
But I agree with you on the algae front. That looks to be the true sustainable one. It will sequester carbon on a rate that none of the other projects seem to be able to do. And it produces two useful things. There's the oil it produces, and there's also, you can use the remainder of it as animal food. So you don't have to cut down the rainforest to plant palm oil plantations.
And in fact, some people are using it for as a wrapper instead of plastics and things like this.
Yeah.
So yeah, there's a lot of things that can be done with algae.
Yeah, I think as well the other interesting point that you raised as well is the emission of water, and what do you do with all of that extra water vapor going into the atmosphere, and that seems to be an issue that's not really been addressed. And what then is the impact on climate? Because actually, the major greenhouse gas is water vapor. That's the one.
Yeah, in my industry, it's I ask people what is the number one greenhouse gas, and they all say carbon dioxide. But no, that's the number one man-made greenhouse gas. But the number one greenhouse gas, as you say rightly, is water vapor. The planet is 7/10 water. So
yeah, and of course, the other thing with water vapor as well is that it's water vapor that provides the energy for weather to be created and destroyed because of the release and absorption of energy that takes place during its changes of phase. So if you're putting more of that there, then actually you are playing the weather machine.
now,
And that's something that's unknowable.
hey, isn't this your job? Or you're going to say it's climatologist and not weather?
Allegedly.
There was an interesting one, actually. Okay, that was reference to hydrogen. And biofuels would have a similar problem, but not to the same extent. They'll just have the problem same as aviation, jet fuel, fossil fuel. But there was one biofuel, and I can't remember what the crop source was, and they noted a significant reduction in the contrails. I can't remember the name of the biostock, but there was a plant that produced much less contrails. And for the contrails to form, they need like a little particle, a non-volatile particle, and then the water can attach itself to that and form the ice crystal, which is what you see. And somehow it's not producing those particles, or producing less of those particles.
Yeah, interesting. Of course, it's estimated that after the 11th September attacks, when all air transport was grounded, the global temperature rose by 2 degrees because of the reduction in contract. I mean, that was the estimate that was made. So there's a lot of factors that go into play. That's not to say that we shouldn't do anything, but it requires probably more careful thinking than the initial
exactly
numbers would suggest.
Yeah, it's very difficult because we're actually starting to mess around with things we don't actually understand.
Absolutely, and it is a little bit like, you see the weather modifications taking place over the orchards and the vineyards in France. Another place in the world, I saw the Chinese were doing some modifications as well. We really don't know if those modifications do work, and I think there still needs to be work done to see if they do work. There will be impacts down the line if those modifications are done on a large enough scale. We can't just go around impacting the climate willy-nilly, although obviously we could say we've done that with CO2 over many, many years. But these short-term changes that we're trying to bring about will have additional consequences.
Yes, and that's the thing, not to undo something, but push something else to the right for someone else to worry about. We need to try and fix it. Absolutely. In fact, this Steve Oldham from Carbon Engineering, the guy who's chatting about the direct air capture, he's got some other interesting videos, and he describes the situation very well. He sort of thinks of it in some terms of a bathtub, which is just constantly filling. I think it was, as Ian was saying, we've been filling this for ages, and I disagree with Ian because I think we've been filling it longer. The industrial revolution was like 200 and a bit years ago, and we've been filling it longer. And there's only so much the planet can take, and how are we going to stop it? We're trying to stop it now, overfilling, and we're trying to do that by turning off a tap and leave it to the constant level. And we need to try and bring it back down. And this is the way Steve Oldham describes it. And I think he actually onto a thing in terms of what he's trying to describe. But what concerns me is how big the plants have to be, how much area they need to start doing all this extraction. And his system there is what he's done. He's been quite clever that he's using a lot of standard parts. It's not specialized parts. It's not an expensive process. There are some core elements, but the general thing is it's mass and easily producible. But that said, I do wonder how big and how long these things have to be running.
Yeah.
And how quickly can they do things like, so he's talking about taking the carbon out there. His system uses a solution, and then he would put that into, you can store that back into the earth through aquifers. And there I'm thinking, yeah, okay for now, but at some point in the future, something interesting may happen. It's like reverse fracking, if you like. And again, how big these plants are and how much fuel they can produce, synthetic fuel from the air they can produce for an airplane, because some of these airplanes, the bigger airplanes, they're taking over 200,000 litres of fuel on the trip. So it's a lot of fuel.
Isn't that the same for the algae, though? They'll need huge areas and huge plants to
Yeah, well, it's only Belgium. I'm quite happy to sacrifice Belgium.
No, Belgium chocolate. Sorry.
Well,
No.
I was waiting for you to say.
And my friends in Belgium.
Yeah, no, that's fair enough. But it just needs an area about that size. Now, it doesn't mean it needs to necessarily occupy land. You could think about putting this out on lakes or oceans.
Don't forget the whales.
Whatever you do, whatever you do, you're touching something and you're upsetting the balance elsewhere.
Yeah, it's got to be a compromise, hasn't it?
Yeah.
Very much like my disclaimer.
Yeah, absolutely. Well, listen, it's been fascinating, and Eddie, thanks for your time, because I know it's getting quite late in Switzerland where you are now, and it's really interesting that somebody who's in an industry which is seen as heavily polluting is doing such work on trying to get things more, I don't like the word sustainable, on a more environmentally friendly footing. Very, very interesting to see the work and the thoughts that are going into that right now. It's probably got to be speeded up, hasn't it? But I think it's fascinating to see how we're finally managing to get these things done. And if we see what we've done with COVID and with the vaccinations and how rapidly science came together with that, I think it does go to prove that with thinking all along the same sort of lines, sometimes out of the box and along the same lines, we can get solutions in place. So Eddie, we've learned so much tonight. Thank you so much for your time. It would be great if you've come to talk and talk to us again. And of course, you did it all in Womban speak, which we all got and understood, and you put across some really difficult concepts. So thank you so much.
Honestly, when I came out here, I was sat next to a guy who ran flight tests from his desk. His name was Peter Ritter. And I was out for 3 months, and my German was safely summed up on the back of a postage stamp. Peter's English was broken, but it was okay. But that said, after 3 months, I was about to go back, and I said, well, it was great meeting you, Peter, cheerio. And he said, now I understand you, after 3 months.
Excellent, brilliant. Well, I think we can probably all say that talk was Boston. So thank you so much. Thank you, Eddie. That was absolutely superb. And please come back and talk to us again someday.
I look forward to it. I would like to go and see my mum when I can. You guys are lucky you've already had your vaccinations. I'll get my first one on Tuesday.
Excellent.
Long overdue, we're slow.
Yeah, well, good luck with that. And if you're over here, Eddie, one of the Thursdays, we meet the first Thursday of the month, you'll have to come along to a meeting and say hello.
I will do.
Excellent. Ian, did you want to jump in there?
Yeah, just going to say to Eddie, surely you can get yourself a holiday in Nepal, because don't they have some airports up there which would only take things like turbo porters?
Yes, and in fact, some of our porters are up there, and there's a famous one called Yeti, which is still up on a glacier or something. But if you're talking about the airport, I think you're talking about, if I remember right, it actually has a mountain at the end of the runway. And it's quite famous because some people can't manage to stop the airplane in time and finish into the mountain.
Eddie, I've just had a very quick, can I take your time again? Another quick question just come in. which says, isn't NOx injected into car engines to improve performance? Therefore, why isn't it incorporated into the jet engine burn cycle instead of being a waste product?
Okay, yeah, it's a good point, because what happens is, and it was on one of the slides where I had to go through quite quickly, it's exhaust gas recycling, and what they do is they cool the temperature of the cylinder head, I believe, and because you cool it, you're not producing the, in fact, from the chemistry points, then you're producing less nitrous oxide, because, as I say, the nitrous oxide is being produced by the hotter temperatures. So from the chemical point, recycling nitrous oxide definitely makes sense. Cars, I don't know why cars are doing it. I'm in aerodynamics. I'm not into engines. I'm not into propulsion. We take engines. We don't make our own engines. But it's very difficult to take the jet stream from the back and recycle that back through the engine. You are destroying the flow, the very thing you need to provide thrust for the aircraft.
Right, got you.
And everything is about maximizing the thrust you can with minimum energy.
Yeah.
So I can imagine from the energy cycle standpoint, it just wouldn't work.
Right. All back to bang for your buck.
Yep.
Yeah. And on that note, Eddie, thank you. That's been absolutely fascinating. Hello from Womben to Switzerland. And thank you again. All right. Cheers, Eddie. If we can all show appreciation, that would be
Thank you for your
excellent.
time. Thank you for your time. Bye.
Thank you.
Thank you, Eddie.
My pleasure.